Hi, my name is Walsh. I'm the lead for Group 2, and today I'm going to be going over what we'll be doing in the jet engine experiment. As you can see, this is the setup that we're using in the lab. This gives you the jet engine in there. We don't have this cover right here for the output, but we do have a vent to take that superheated air away, which is convenient so it doesn't burn you. So I'm going to be going over just some background about why this experiment, why it's applicable to us, and what it's about, what the cycle that's related to is. I'm going to be going over the relevance of the jet engine and the Brayton cycle that it's founded upon. I'm going to be going over what the experiment entails, kind of lightly, and I'm going to be going over the equations. I won't be doing example equations because the data that I could use for that was not online. I will go over the theoretical analysis though, and a conclusion after that. Alright, so for our experiment, this is a kind of a cross-section of the actual engine we'll be using. As you can see, there's sensors all over the thing. You've got temperature sensors at the opening, you've got temperature sensors both at the, in all the chambers, the combustor, the axial turbine, at the converging nozzle, right at the end here. And you've got an outer, you got temperature sensors everywhere. You've got one up here right outside of the axial turbine. You see that's right up against the edge. That is a pressure sensor. You can get the stagnation pressure in order for you to do your calculations. So you have a stagnation pressure coming right there. You have the pressure at the exit, and using those two, you can get data about the exit flow. You've also got pressure within the combustor and pressure entering. And so that's our setup. After we get the engine up to about 45,000 RPMs, it can sustain itself without the use of the compressed air to spin the turbine. At that point, we take it back down to 40,000, and we do measurements at about 5,000 RPM or whatever we need in order to get these measurements, and also 5 additional measurements at our own choosing locations. So after we get all those measurements, we have all the data recorded for the temperature and the pressure sensors. And we can use that temperature and pressure data in order to calculate the thermodynamic properties that we are actually concerned about, like the performance, the efficiency, and such. These are some of the equations that are going to be relevant to our project. You can see the mass flow of the air is definitely important. You have the thermodynamic properties like the heats, these specific heats of the air that's going through. You have the heat introduced by the fuel, which we don't see much of because we're actually combusting it, so that's what we're concerned about, is the energy you get from that combustion. And so that turns into the velocity of the gas as it's going through. So you've got a stagnation temperature, which we don't hear very much of. We hear stagnation pressure more from fluid dynamics. There's a stagnation temperature, which is your static temperature, as well as the component of the velocity with the coefficient here, the constant pressure. And so you've got your stagnation pressure, which is your total pressure. That includes the static pressure that you would get on a gauge, as well as the pressure that's derived from the velocity. So it's like 2 energy components. And then you've also got the heat added, Q added, which is what you're getting from your actual fuel as it's being combusted. So you've got the mass of the air coming in, you've got the coefficient of heat from the air, and you've got the temperature difference between the very last section and the very beginning section. So that's going to be your total heat added in the entire process. And we know that comes from the fuel being combusted. One of the more important ones is the thrust. That's how we're going to actually, one of the main ways we determine the efficiency of a jet engine, because the thrust is what we want, it's the result. So you've got the velocity V5, which is coming out, it's the 5th section of the engine, is the exit nozzle. And that velocity is your thrust over your mass flow rate, so you can easily use that to determine your thrust. Your combustion fraction energy is the friction energy of your, it's the heat of the combustor over the heat of the fuel, so it's like the efficiency, how much energy are you getting out of this fuel as opposed to how much energy is in the fuel altogether. Like that chemical energy, you're not going to get all of it, you're never going to get 100%. So you've got that combustion fraction energy, which is important, another part of your efficiency. The fraction of fuel burned in the nozzle, there's also going to be some fuel that makes it through all the way into the nozzle, and that can't help you add your speed, so you account for that here. And so you've got the heat of the nozzle as well, taking that into account. So the temperature at the end of the nozzle and right outside of the turbine, because there's going to be inside that nozzle section some combustion. All right, you can get that fraction at the bottom. Another important thing that we use for efficiencies is like the efficiency of the compressor or the efficiency of the turbine. So you can determine the work you're going to put into the compressor, the heat of the turbine, the work of the turbine that you're going to put in, and you can use those to determine how efficient they are in your cycle. And you can use the fractions that you got earlier conveniently to help determine those. All right, just some background about the Brayton cycle. Here we have a specific jet engine Brayton cycle where you've got, normally, if it's a ideal condition, you would first raise it isentropically, and then you would isobarically add energy to it in the combustion chamber, in the combustor. And so that raises your temperature, and then after that it gets released into the turbine, and so you've got superheated, somewhat compressed down gas that's going to shoot out of that turbine, it's going to spin the turbine, which puts work back into the entire process, spins the compressor. And so then after it goes through the turbine, right here, you can see it goes through the nozzle and kind of picks up a bit more energy from that fuel that escapes into there. It picks up a bit more speed too, because the nozzle is converging, and a converging nozzle, as you know, if it's a subsonic flow, it's going to increase the speed of that flow. So then after you've got the, after it comes out of the nozzle, it returns to the atmosphere. You don't really have a direct connection there. But that makes up the Brayton cycle for this jet engine that we're looking at. It's very relevant to us because jet engines and turbo machinery provide high thrust for their weight. We're always looking at getting more for less. And jet engines are ideal for use in aircraft for that reason. You can't have a heavy aircraft expected to be very efficient. Also, yeah, they're efficient in the upper atmosphere because of that low pressure. There's not much else that works that well in the upper atmosphere. Just because of that low pressure, that is ideal for a jet engine. The Brayton cycle is relevant for us even outside of airplanes, though, because it has practical applications in turbines to move fluids in turbo machinery and such, not just for air. Here's the theoretical analysis I was able to do. The fuel calibration curves, I use a second order polynomial because if you look at the data points, it fits them all, it fits both of them well. Like without any other type, like if you'd done logarithmic or exponential, you would not have gotten a coherent pattern there. So it's shown to be nonlinear, and you can see that of the two of them, you've got the RPM curve and you've got a fuel motor curve. So those are two data values that you're taking in, but only one of them is going to be more usable. Only one of them is going to be really accurate. You can see that the data points of the fuel meter line up almost perfectly with just a second order curve, whereas for the same second order curve, the RPM doesn't match up exactly. So we would use the fuel motor millivolts fuel meter readouts for that calibration curve. All right, so going on to the theoretical analysis, you want to find the exhaust velocity. That's important because it's going to be what's pushing your aircraft or pushing the fluid if you're using it for turbo machinery. So you've got mass equals the density times the mass flow rate equals the density times the velocity times the area. It's basically all of that from fluid mechanics. So the exit velocity can be found as the mass flow rate divided by the density times the area of the exit. So then we can also find another method of finding that exit velocity. We have our stagnation pressure, which is the total pressure energy, basically. And that's the static pressure plus the velocity component of our energy there. So if we solve for that velocity, we get the square root of 2 times the difference between the two pressures, P4 and P5. That's right next to our turbine and right outside our turbine, into the nozzle, divided by the density at the exit. All right, then we've got the third way that we can measure and determine our exit velocity is taking the thrust that we find from that push bar, the thrust bar, and dividing that by our mass flow rate, which we found earlier. And so you can plug that equation back in and get the exit velocity is the square root of the thrust divided by that density times the area of that exit. So according to the equation for thrust, you can find the effect of the pressure right behind the compressor and the pressure before the compressor. So we already know the thrust is the velocity times the mass of the air, but you can also plug back in and get it's the mass flow rate of the air squared divided by the density times the area. So substituting mass flow rate back in, you can get that the total stagnation pressure equals the static pressure plus the velocity component. And if you plug in, you get it's the total stagnation pressure is equal to the static pressure plus the mass flow rate squared divided by 2 times the density times the area squared. So that means that if you're increasing the pressure at the end of the compressor in relation to the pressure before, increasing that ratio of P2 over P1, you're going to be adding to the stagnation pressure, you're going to actually be adding to the energy. So you're going to increase that mass flow rate, which is going to increase the entire energy output from the flow. So therefore you are going to actually increase the thrust, because that's what the thrust depends on, is that flow rate of the air. So in conclusion, the jet engine is a practical example of the Brayton cycle. It is greatly relevant for aircraft, but also for other turbo machinery, so you can't just discount it because it does really well at moving fluids. This experiment will show us, when we conducted, that the Brayton cycle, it'll show us that in action, it allows us to analyze its thermodynamic characteristics, like I just explained, and you can even get some hands-on experience controlling it with the throttle lever, so you actually get to control one of these thermodynamic cycles that we've been learning about all the time. All right, thank you.